But even if you don't need a mark, and if you have remarks or anything, I can correct anything. Anyway. So, maybe a word on symbolic dynamics and groups. So, we saw subshift.
I have a question about that, about the first task. The perfect set is, we assume that it should be closed, or only if do not have an isolated point.
But I said perfect, compact.
Yes, compact, but in one of the first problems there was to find an example when we have uncountable perfect set that is not compact. Should we assume that this set is closed, or we can show the example where when we have not closed set without yes.
I think
because in Wikipedia the perfect set is closed and without a isolated point. And
sorry. Okay. Sorry.
I couldn't.
Sorry. Yes. Sometimes there are differences between definitions, also in English, in French, or in different communities. I didn't think about this specific difference. So, but I think on the paper, so if I put a definition, maybe there are also other definitions where it may be different with respect to. So yes, I should have been careful and maybe not say perfect. Sorry. Will it have changed something, or did you still answer it?
I couldn't find non-compact but closed set that is countable, but
okay, so
no isolated point.
Okay, sorry. Yeah. Okay. So yes, we saw subshift on Z, subshift on Z2, and the natural thing is to. So what do we need to talk about subshift?
Another question. Should we prepare some problems for tomorrow from the exam, for example? If we will not consider them today, then
yes, you can bring me additional problems, and
if we can.
Yes, and if we discuss about them today, then I will see. I will see it.
Of course.
And if we didn't, then it will count as a bonus. Yes. Yes. So what do we need to define a subshift? So in the topological definition, we have a set which is invariant by the shift map. The shift map, what is it? Something where you need to take a configuration. And we wrote something like this. So the set of indices should have this map first. So a natural setting is that these indices are in some semi-group or some group. So you can define a subshift inside something. For the topological version, it's not. The topology on A to the G is not different from A to the Z, because there are more counter sets. And the shift invariance, you can write it like this. So maybe if you don't have something commutative, maybe you want to write it with some multiplicative notation rather. And this makes sense. Okay? So, often you will see in, for example, in the book by Barsheim and Cournart, which is devoted to subshifts, no, not to subshifts, to cellular automata on groups. You will often see a definition with a -1, which allows to speak of a less action, but it doesn't fit completely the definition in memory in subgroup. You can also define this, then if you write correctly, maybe the action goes to the other side or something. Anyway, this makes sense. So, what does it mean? So, and by the way, the characterization of subshifts in terms of patterns also works, and the characterization of factor maps of homomorphisms, shift homomorphisms, in terms of local groups also work. So, what does it mean? So let's say, for example, we can take the free group. The free group has a Cayley graph which looks like this. What is a Cayley graph? It's an infinite graph, possibly infinite, so the group is infinite, because the set of vertices is the set of elements of the group, and the edges are labeled by a set of generators. For example, here I have two generators, A, B. Let's speak only about group. Let's forget about semigroups, but there is a larger setting about semigroups. Let's speak about the groups. If you look at the free group generated by A and B, you have the neutral element here. Then if you go right, you have A. If you go up, you have B. If you go down, you have B minus 1. If you go left, you have A minus 1. And then if you, once you are in A, you can do exactly the same operation. You can again do A, B, B minus 1. If you do A minus 1, then you go back to the first element. And the fact that it's a free group tells you that you cannot meet any other points that you drew from other branch, because otherwise it would mean that you have a relation in the group. Here, the only way to do a cycle in this graph is to come back at the same point. This is exactly equivalent to being a free group. There is, because cycles in the Cayley graph correspond to relations between elements, between a product of elements from the generating set. So, now a configuration on this thing where we put colors on the graph. Each point, each vertex of the graph. Is it clear for everyone what is this graph in general for a group? So the graph of Z2 is exactly a grid. But we put the colors in the vertices. But you agree that it's really equivalent to putting them inside by changing the point of view. The line is the Cayley graph of Z. Well, there are more complicated Cayley graphs, but I don't want to do a full course now because I think you've had enough of formalism during the week. So what did I want to do? So you can define, yes, just cellular automaton, what is it? You can define also topologically a sheaf commuting continuous map. And there is this characterization in terms of local rule with respect to a neighborhood. So basically, it's the same intuition. You have you can say you have some kind of cell in some state at this vertex, and it wants to evolve, and to evolve it looks like the neighboring vertices. Let's say that you have radius 1. In the rule I have radius 1, you just look at the neighboring vertices, the state they have, and depending on this, you adapt your state. Okay, now,
why do we demand that our G is free group?
No, we don't demand, it's an example.
And what is the shifted rate then, or equivalent in this example?
It's the shift, it's called the shift also, defined by this. So, you see that you have here it's a shift on the left. You will have a shift on the right also, which is different when the group is not abelian. So here, if I shift, when I just say on the right and on the left, I don't mean about the A and B, I mean the left action or right action. So, for example, let's talk about the shift with respect to A, I equals A, of such a configuration. Then one of the two, either the left action or the right action, I prefer to say this, I don't want to say something wrong, means that it's like you're some guy here and you just move here, and now you look around you and you think that you are in the center of the graph. You see that this looks exactly like the same graph. We don't care about the length of the edges. It's meaningless. I just put shorter lengths just so that they don't intersect here, but the lengths are not relevant. So here, the graph centered here is exactly isomorphic to the graph centered here. It's a property of all Cayley graphs of all groups. Yeah, even a larger graph, quasi-transitive graphs. You could also apply such shifts here, but Cayley graphs, because you can do the same, you can multiply by the same words in everywhere, then it looks the same. In a Cayley graph of a monoid, it's not exactly true, except that in some sense you think that you see locally that it could, it looks like you have as many directions where you can go, because you can multiply, but possibly some of them have shorter cycle than you had originally. But let's forget about this. Let's focus on groups. And so, when you center the graph here and you look at the new coloring that is induced by the original coloring, but when I center here, then this coloring is the tiling configuration of the full shift, which is the shift of the previous one by A. And it's either the left action or the right action. And the other one is more complicated to see because it's not about moving. How can you see it? Well, okay. So let's concentrate on this one because the other one is much less interesting. Okay. But what can you do on a free group? You can, for example, you can define a Taylor automaton which the local rule here has this neighborhood. So here there is a neighborhood, a finite neighborhood in G, and there is a local rule which takes as input coloring from the neighborhood and gives you one color. And f of x in I is equal to f of x I, in some sense, up to renaming the indices. So every cell, for example, here, in this example, B equals 0, A, B, equals 1, 1, 1, A, B. So every cell looks at its own cell, its own state, the state of its right neighbor, the state of its left neighbor, of its upper neighbor, sorry. Okay? For example, here, this guy, we look at what happens in these three cells. And depending on these three states, it applies, for example, this local rule. A equals this over 2B. I can do an addition of the three states, and it gives me a new state.
Are there any restrictions on the state?
It's finite.
It's 0.
Yes, like in D2, it's finite, but you can always recode it. If you recode and you do a grouping of your subsheets, you can impose it to be a subset of your generating set. The equivalent definition of nearest neighbor subsheet, it's not the equivalent, it's the generalization. You can say that a subsheet is nearest neighbor, or a cellular automaton or a homomorphism is nearest neighbor if the neighborhood is a subset of the generating set. So the nearest neighbor depends on the generating set. Here I put a definition of cellular automaton which does not depend on generating set, but for every generating set you can recode your original subsheet so that the cellular automaton is a composition of a grouping and of a nearest neighbor cellular automaton for the least generated. Okay. So now, what happens with this example? This guy takes some information from the right, some information from the top, poof, it does the sum, and it adapts the cover. Do you think it's surjective, injective? So
It's not injected.
it's not injective, but it's surjective. The idea is really the same as in, we saw the Z example more or less of this in some session. Are you ready? What happened? Okay. There is some video where we could, it was maybe on the right of the blackboard at some point, and we drew some space-time diagram of the cellular automaton, which does the sum of two cells, and gives you the next step. This is not surjective because you always, not injective because you can always, because two configurations
Go to the same image.
yes. So basically, if you take this configuration and at each vertex you change two, well, you can easily build two images for the same image, but it's surjective because it's also easy. So now. So, what I wanted to focus on, but I'm not sure how complex it is to do it now, but in this free group, there are examples of cellular automaton which are injective, which are pre-injective, but not surjective. Ah, so you didn't do this exercise in the... So, it was in the exam.
What's the difference, if I'm mistaken, in homework, pre-injectiveness implied subjectiveness, but what's the difference now?
Because precisely, amenability. I will focus on. It's not what you proved. It was on cellular automata on Z. We talked only on Z. Here you have a cellular automata on some group, and I will
Z is different from this free group.
Yeah, and we will see it was exactly because your camera asked me about amenability. So this is exactly the problem. Or this problem, or the interesting thing. But let me recall what is pre-injective. Pre-injective means that f of x equals f of y implies either x equals y or the number of differences in x and y is infinite. So it's nearly injective, except
Some very far point.
yes, not in terms of the topology. So in particular, injective implies pre-injective, but you also have, for example, in Z you have f of xi equals xi plus xi plus 1 modulo 2. That was the example. If you want, so we write x and f of x, and maybe you want to write y, right? And f of x equals f of y. Okay? Then imagine there is a difference between x and y. Otherwise they are equal. So here you have 0 and here you have 1. But you must have the same, here in f of x you must have the same number. So alpha. So let's say alpha equals 0. It's the same if it's 1. 0, which means that this is the sum of this and this. So here you have a 0. It's also the sum modulo 2 of this and this. So here you have 1. And here you have also some alpha. So here you have alpha minus 0. Here you have alpha minus 1. They also differ. So actually you see that the two primitives must be different everywhere on the right. But here, it's not projective. So it's objective. We saw that it's not injective, but it's even not projective.
Do you have equivalence of projectiveness here and injectiveness on all words that have infinitely many zeros? Or
not infinitely many zeros, but
on the left,
no
yes,
zeros.
non-zeros, yes.
Yes, this is true.
So we can prove this, but we're trying to prove that this is not projective. We can.
Yes, you're right. So let's try. If you have one. Yes, I should have prepared that. I didn't know we were going to speak about this. But
we can show an example.
Yes, but if you find it, it's good. Let's change. Yes. Okay, now let's change the definition. Now, let's say that it's not a Celer automaton. It's a homomorphism which changes the alphabet. So remember homomorphism. But F is not, can change the alphabet. So here I map this to the pair XA, XB. So actually I can even remove this from set V. It's not very important. It's a pair. So here F is from Z to from A to squared into 12 A squared. relation is A to the G, and gives a proof relation is A to the G. At each vertex, I put the pair of the two. So this is clearly bijective. Because you can recover from your neighbors, you can recover your former okay, I should have prepared, I think no. Okay, let me try this. Now, this is an interesting example, but for something else. But this example shows that there cannot be a definition of entropy, a good definition of entropy, because you can increase it by factor math, which is something that you usually don't want. And by conjugacy, you can even increase it by conjugacy. So it's not even a conjugacy invariant, so it's not a natural dynamical notion. But let's come back to the, okay, so 0, 1 squared to the G to itself, okay? And the local map is going from 0, 1 squared to 0, 1 squared to each x a 1 x a 2 x b 1 x b 2. I take x a 1 plus x b 2 modulo 2. And this is the objective.
It is not a map to square of.
Sorry, yes. And xb1 plus xab2. Okay. Now let's do something else. I'm sorry, I didn't prepare this particular question because I didn't know we would talk about this.
But maybe
just the intuition, if you want.
I'm sorry, but I do not know the definition of amenability.
Yes.
Perhaps I'm not the only one.
Yeah, no, I know you don't. And the definition is very hard, and this is why I wanted to show some intuition. The intuition of the amenability is that you have a graph like this, such that when you start from, so there is a natural notion of balls in the graph, of distance in the graph, which corresponds to taking the length of the word, well, it's the distance in the graph, okay? So you have balls starting from 0. So in the first ball you have these 4 sets, 4 vertices. In the second one you have basically all the ones I drew. Yes. In the third one you would have also additionally all these ones. Okay. You have a notion of balls. How does it grow? Here it grows exponentially because it's essentially this group is if I just look at half of it, just this part, it's exactly the number of words on this alphabet. And if I look at everything, it's the number of words on alphabet A, B, A-1, B-1, which do not contain something that can be erased directly, like A-1. Okay, it's a reduced word. So it's this number of words includes all words on AB, for example. So it's like the number is at least 2 to the n. And this is a big difference with Z and Z2, where the number is, if you have a grid, well, the balls correspond to squares actually. It's the number of points that you see at distance 2 from this point, for example. Then you have exactly this. You have 9 points. And at distance 3, you have 16 points. So it's quadratic. So this notion of growth in group is very important. But even more importantly, what is important here is that if I look at all the points, if I take a big ball, I look at the number of points inside and the number of points in the boundary, then the number of points in the boundary is not neglectable. If you look in Z2, you take a very, very big square. Here you have a linear number of points in the boundary and a quadratic number inside. So essentially, after a while, the boundary is neglectable, and you use this for those who dealt with the Garden of Eden exercise, even though it was not in V2, but the thing was in Z, and at some point you will have a computation of entropy to prove that the cellular automaton is or the contrary. These two arguments with equivalent. This entropy argument strongly uses the fact that you will have bigger squares and the boundary will be neglectable. And the definition of amenable is equivalent to saying the boundary is not neglectable. And in particular, if the boundary is not neglectable, you can do exercises, you can do examples like the ones I was trying to do, excuse me, that I didn't manage, of something where you have many informations coming from several ways and getting to the middle, and so you see here that with a cellular automaton, all the things that are far from the exterior, they will essentially give you the same pattern. If they start from a big pattern like this, they will give you the same thing. But here you have a very a small amount of these which are really in the interior. So the state of the whole equivalent of the square, the state of the whole ball can change a lot in one step. Here, if you take a very big ball, the state cannot change a lot in one step. Only the boundary can change. So here, with example a bit like this, like the sum of two things, you can take information from above and from the right and do something with it, and do something non-injective, which is surjective.
But the language does not grow very fast here. For example, in shifts, full shifts, for example, we have exponential growth of our language. And here, if we use naive definition of entropy, what will happen?
It's double exponential.
It's double exponential. If you take, for example, two logarithms, like in definition of entropy, we take logarithm of the size of the language of
But the problem is that you, for example, in the definition of entropy, you are happy to say that the entropy is a limit, okay, and not just an infimum.
Yes.
And why is it a limit? Because we use something like the Fekete lemma.
Yes, yes.
And how does it work, Fekete lemma? You prove that there is some. So you prove that if you take the number of patterns here, then all of these are, there are small patterns here that are all allowed, and so you can bound the number of big valid patterns in terms of some power of the small patterns. But here we are using the fact that it can be covered with not so many of them. Here, the number of little squares to cover a big squares, it's no more squares here, but if you want to cover, then it's exponentials, even this. So of course the definition with just infimum can work, but it's not even, in some sense, it doesn't work fine with the shifts, because if you shift something, you may find something completely different. And in particular, it's not a conjugacy invariant. So something which is not a conjugacy invariant can be interesting combinatorially if you are interested in wild-tiding, something maybe, but in our setting, in dynamical system theory, it's not relevant to have something which is not conjugacy invariant. It means it's not something which depends on the dynamics only, but on your encoding of it.
So, to sum up, if we take double logarithm, it will not work. We cannot prove that we always have limit. We only will have.
No, you can even prove that you don't have a limit. I mean, you can even prove that in some cases you don't have a limit. But recently there has been a theory of Sophic entropy which applies to a bigger class of groups, but then this entropy depends on Sophic approximation, which means that you approximate your graph in some sense by finite graphs, and it works for every Sophic group, and we don't know if there exists a non-Sophic group. So
it works for three groups.
This definition of entropy, but it's not exactly the same as I gave. You have to take in. It depends. Possibly, it can depend on not only on the group, but on the approximation, on the sequence of approximation that you take.
If we have non-amenable group for very simple Z, will two definitions coincide?
Yes, of course. So, Sophic entropy, when you apply it to amenable groups, you can show that it doesn't depend on the Sophic approximation, and that the entropy is the same as the classical one. Yes. So that's the point where I don't know if you want the definitions, a formal definition. So in amenability, you have actually many equivalent definitions. One of them is that you have an invariance measured on the group, which is invariant by the multiplication. A second of them is that the one I gave, that you don't have let's say that a group is non-amenable if and only if you can find a sequence of finite sets which is growing and spans the whole group. Actually, no, you don't require it to span the whole group, which is growing, and such that the boundary, the size of the boundary, you can define it, the size of the number of points in this set which have a neighbor in the graph which is not in the set. And this size is not a small o of the whole size of the set. There is also the equivalent definition of the paradoxical decomposition, which is the one based on which the Banach-Tarski paradox is based, which says that you can, if you look at this graph, you can cut it into two, for example here, okay, and then I map isomorphically, in graph isomorphically, out of this part, I can map it only here, okay? You agree? All of this half is the same as here. And then this one is, and then all of this, and then if I change A to B, I have the same here, and I have the same here. So, in some sense, G can be decomposed as G1 union G2, such that there is this G H, let's say G1, G2, G3, G4, such, and maybe graph isomorphism. Such that G is also the union of, let's say this is a graph isomorphism, so Gi, the translation by Gi of G. So you cut it into two, then you apply some shifts, some translations, and you have four equal parts. This is disjunct union sign. Okay? So this is some kind of paradox. It's pretty much linked to this is non-amenability, sorry. And this is pretty much linked to the fact that you cannot define a measure which is invariant by the multiplication. And this notion was introduced first by von Neumann, and it has it is exactly the boundary of many interesting properties, like natural properties in dynamical systems, like the definition of entropy, like the Gardner-Leonard theorem. By the way, von Neumann is also one of the fathers of cellular automata, and I think at his time he didn't realize that there would be such a merge of these two topics. Yeah. So, for every non-amenable group, you can find a cellular automaton which is pre-injective and not surjective, and you can find a cellular automaton which is surjective and not pre-injective. So both implications are equivalent to amenability. But injective implies surjective is true outside. Just injective, because injective is stronger than pre-injective. So, why is it true outside? So, inside a amenable group, you can show it by the Gardner-Leonard theorem. It's very close to the proof that some of you did in the exam, because you have a good notion of entropy. There are several ways to see the proof, of course, but the easiest way is maybe to say that you have a nice notion of entropy and such things. but injective implies pre-injective is also true in residually finite groups. Residually finite group means that there is basically you can approximate it by finite groups.
So there is no ergodic theory for non-amenable groups.
Good question. So ergodic theory usually Z. There are generalization of ergodic theorems
For amenable
groups, yes. And only recently there is this theory that goes out of amenable groups. But for example, in a non-amenable group, for every non-amenable group, you can find a dynamical system, which is an action of this group, a continuous action of this group, which has no invariant measure. This is false in amenable group. I think there was an exercise where I asked you, maybe I didn't ask you exactly this question, but a continuous action of Z on a compact space always admits one invariant measure. This comes from compactness of the set of measure, probability measures. And you apply compactness to your sequence to your orbit of the measures in some sense. But this is no more a sequence when you deal with group actions. And it can be, this theorem can be generalized to a minimal group. It's no more a sequence, but still it grows nicely. But if you go out of amenable group, then for every non-amenable group you can find one compact set on which it acts continuously and which has no invariant measure. This is also an equivalence for amenability. And what I was going to say, yes. So to go out of amenable groups, yes. An example of residually finite group is the free group. But it's not very easy to see it, especially since I didn't see the definition. So we will look at what happens on Z2. So basically, the fact that Z2 is residually finite corresponds to, I will give you the intuition even before the definition, corresponds to the fact that the grid can be approximated by tori. So if you take up bigger and bigger square and you say on top and on the bottom I paste, and on left and right I paste, then you have finite group. This is a finite group, the torus is a finite group. But you can more or less be convinced in some sense that it approximates the grid. Formally, residually finite means that for every, so there are also many equivalent definitions, so which one will I give? For all finite, maybe not F, because F is usually, for all S finite, there is a finite group such that, and the homomorphism of group such that X does not intersect the kernel of phi. So this is for those who want formal definitions, but let's come back to the example. What does it mean? You choose as many points here, finitely many, as you want, but as many as you want in the grid, then you can always find a big torus. You can always fold further away so that you map to a finite group, but you didn't lose the information of your point. This is exactly this. And in that case, the full shift on a residually finite group has a dense set of periodic points. You can see more or less the intuition. You can close as a torus, and whatever you chose as a cylinder in the middle, you can find a torus later, which actually will correspond to a periodic configuration when you unfold it in some sense. And injective Taylor automata or surjective must be injective on periodic configurations for a reason of because they are finite configurations of bounded, finitely many configurations of bounded period. So if you deal with every so you fix a maximal length n. The set of periodic configurations with period some vector which has length n is a finite subsystem of a Euler automaton. It's a finite subsystem of an injective system, so it must be injective, so it must be surjective. And surjectivity on the periodic configuration gives you, by density, gives you the surjectivity of the Euler automaton. So you have two very different proofs to prove that injective Euler automata are surjective. You have one which works in amenable groups, one which works in residually finite groups. And this is the main idea, because we don't know when this doesn't hold. I think it's a question by Gromov. That there exists one group such on which CA, injective CA are not surjective.
We consider only groups with finite number of generators.
So in his yes, let's say yes. In his definition, in the definition, then if you take this definition of stellar automata, it has a finite neighborhood, and everything happens in the group that is generated by V. So you can restrict the question to finitely generated groups.
But this question about residually finite.
No, it's not about residually finite.
Yeah.
So if there is a group, it's equivalent, because if you take this definition, then it's injective if and only this kind of layer which is in the group generated by V is injective, and the same process. Everything happens in the group generated by V, it's really equivalent. If you want, you can say finitely generated. So, in the residually finite group, we have a proof. In the amenable case, we have a proof. And
these sets, amenable groups and residually finite groups, are not one contained in another. They only intersect. They
intersect, but then there is a proof that builds upon the class, which is a generalization of the two of everything that you can build by products, by super groups, whatever, from these two classes, and this is the Sophist groups. I think this name comes from Benjamin Weiss, and we know that this is true in Sophist groups. But we don't know if there is a non-Sophist group. question is still open. What is a sulfide group? Here, you really don't want me to give the formal definition, but the intuition is your graph, very distant intuition. Your graph can be approximated by finite graphs, in the sense that there is a graph homomorphism such that which maps your group for every finite set of your graph, there is a graph homomorphism to a finite graph such that the boundary, the place where this homomorphism does not correspond to a group homomorphism is neglectable. So maybe it's less interesting that I repeat this attempt to define than to say why it's true in residually finite and in amenable, so that you have some kind of intuition. In amenable groups, which is not the case here, in amenable groups, your finite graphs, yes, would be big squares, for example. Okay, this is a bad example because it's also residually finite. But forget about residually finiteness. Imagine you have a group which grows not very fast, and it's not residually finite. But you can take a finite graph by just getting rid of everything which is outside of your big ball, and then it's nearly a group because you know that the boundary is just an epsilon of the interior, so it satisfies directly the definition of sophicity. But in residually finite group, what you do, imagine you have a residually finite group which is not amenable. I'm sorry, I don't have natural example, but it would take some time to give you some natural examples of such groups. But imagine you have this property of residual finiteness where you can fold the group to have arbitrary extensions. Then you do exactly this to get a new graph with a morphism to, for example, to a tori, from the grid to a torus. And even if the boundary was not neglectable, since you fold in some sense the boundaries because you can do it in a residually finite group to get approximation, you get some finite graph which gives you approximation. I don't know if I want to get too much into detail after the week of exam that you have.
Why this group is not residually finite? Free group.
It's residually finite.
Finite. So
it's a good example, but just it's not so obvious to.
But why every free group with finitely many generators?
It's residually
not. But how can we imagine a group which has finitely many generators, but which is not residually finite? If
every group with finitely many generators can be represented as some free factors.
Factor, yes, of free group, and
no, of course it's not residually finite. It's not factor. It's not preserved by factors.
So we can construct group with finitely many generators which is not residually finite?
Yes, of course. What is this? What is the easiest?
So each free group is residually finite, but the group is not.
Yes, but yes, of course, because otherwise we would know it. No, not everything goes through factor maps. Yes.
For example, some group from finely generated is not finely generated, and it's kind of similar.
Yes.
Catholic. I don't know where you want to go now. Yes, maybe. Do you want me to continue to speak about groups? But say something different. So this is about cellular automata, but if we speak about subshifts, there is a very so if you want to define SFT, you can define SFT also on every group, and then you can ask, can I build an aperiodic SFT? We saw that it's not possible in Z, but it's possible in Z2. So where does the border lie?
We define a periodic subshift if it has no...
Subshift of finite time, sorry.
Yes, subshift of finite...
It's not empty, but it has
no
periodic...
No periodic point, yes.
So in Z, all subshifts of finite type are not aperiodic. So the domino problem, the timing problem, the emptiness problem of SFT is decidable. In dimension 2, it's undecidable, which implies in particular that there are aperiodic SFT. Where does the boundary lie? And here it's a different question. Just one word on the fact why it's different, because it's static. Here, when we talk about cellular automata, we are also dealing with if you want, the object we are dealing with is a dynamical system on this, which means that if I want to draw a space-time diagram, I have a picture like this, and then after one step I have a new picture like this, after one step I have a new picture like this. So in some sense, the object we are dealing with when we are looking at cellular automata on groups corresponds to a product of the group by Z or by N, if you have a number of cellular automata. So, you see more or less? So, but if we are dealing with static things, with subshifts, a very relevant property is the property of virtually free group, sorry. Virtually free group means G has a free group, a free subgroup of finite index. So Z is virtually free, and you know that the emptiness problem is decidable. Here, if you have an SFT on the free group of order 2, you cannot build a strongly aperiodic subshift. You cannot, basically, there are not enough interactions between the branches to embed some computation. You cannot say, okay, you're gonna you compute, let's compute, and then but they don't interact each other. So what worked in Z2 was the fact that you can have a Turing machine which does some stuff, and the fact that actually when you draw a space-time diagram of a Turing machine, the time commutes with the space in some sense. So you have to have a relation in your group. But here it's too simple, and you can prove that it can be proven that...
I'm sorry, is a free group
virtually free?
Virtually. How we construct H?
H equals G.
We multiply G by H.
No.
It's index. Index.
The index of H in G?
Yes, I understand.
H equals G. It's just a little more general than free groups, but essentially the thing is that if you take a free group and you multiply it by a direct product with a finite group, it doesn't change, it nearly doesn't change anything dynamically. You agree? It's nearly, from far away, it's nearly the same, especially in terms of computation. Actually, you can even encode, if it's really a direct product, you can even encode any subshift into a subshift of the free group because you, yes, by some grouping thing, which has the same properties, nearly the same properties, because of course you lose a little in the action, but yes. So these groups are simple in terms of SFT that compute. Basically, we can say that they have the power of computation of finite atom dot. These groups are complicated, but we don't know exactly where the boundary lies. We know that for every virtually free group, the emptiness problem of SFT is decidable. We even know that a whole class of logical, a whole fragment of logics, monadic second-order logics defined, which is like a class of sentences that you can write on subshift by talking about neighbors and talking about colors. This is decidable. It includes the emptiness of SFT. This is decidable on virtually free group. And we conjecture that on every non-virtually free group, it's not decidable, but it's not proven yet. It's proven on many small classes of groups, but not on the whole class. More questions? Basic questions are also accepted. This was not very precise or formal. Maybe just to give you an idea of what's going on. Even before talking about the decidability of the emptiness problem, you can ask, when can I force something aperiodic by just imposing local constraints, which is the case in D2, it's not the case in D, and it's not the case in any free group. So, if you do have another question, I wanted to show you some. What time is it? 20 minutes. What can I show you? Okay, to start with, I wanted to show you just some evolution of cellular automata. Maybe to start with, just the game of life. You know it, but you have already seen it? think about more questions or any question. So yes, I cannot. So it's a very classical. You can come here. It's a very classical exercise that many programists know because for them it's a classical example to. So you start from a very random configuration, and you have these things that happen. So basically, John Conway defined this in the beginning of the 80s, I think, and okay, it's completely random. And then he saw that you have such things that happen. Sometimes you have some messages, some gliders that go like this. And the rule is very, very simple. It can be interpreted as saying that these white things are alive, and if there are too many neighbors, then they die because they don't breathe. If they are not enough, they die of isolation. But if they are exactly the good number of neighbors, then they survive, or they can give birth to someone. And later, some people proved that this was Turing powerful in the sense that you can draw the initial configuration in some sense in such a way that it simulates any computer. It depends on the model, but you can simulate circuits that compute some logical functions and everything. And you can see this by having these little things, little gliders.
And the main difficulty when you program this thing is, from programming point of view, it's not difficult.
No.
But maybe, or I thought it's more, you consider every cell in your rectangle. Maybe it is difficult to compute. Or, I mean, you can. If we simulate the game of life, every step we should consider every cell, every pixel,
Yes.
And decide whether the cell.
You look around, so you have some kind of
Yes.
But window, and it's really not very difficult.
But it works slowly. If we should consider every, maybe.
Yes. Because you want to.
I think in modern software they divide into some grid and look that nothing happens on step, nothing will happen there in any other step. So it dissects into segments.
Logical operation, anyway.
It depends on the software. In this one, they don't do it like this because it's designed for any kind of serial automaton. But you can download also Golly, which is famous, which is most famous probably. And Go comes from Game of Life, and it's designed for this. So you have many optimization, like what you said. Like okay, we know that you have hash tables to go very fast. But you see, this one is programmed quite naively, and still you. Okay, that's another. Okay. Look at something else. So I think. Okay, this is a one-dimensional cellular automata, and you see the space-time diagram. And this has more or less the same property as the one which was written here with the sum of two. That if I change something in the middle, you see what happens? here, when I click, it swaps one white cell to a black cell, or the contrary. In the initial configuration is here, and this is time going up. And if I change, you see there is some kind of speed of message going right and going left. It changes a code like this. And you can so these are, maybe it's small for you to see.
On the left and on the boundaries, we have we assume that we have no neighbor.
I think it's right.
It's yes, it's periodic. Otherwise, if you let a long time and you want a bigger and bigger part of the initial configuration, it's too big. Okay. So you have some kind of everything. So this has a property of expansivity, which was also mentioned in the exam, I think, which means that if you change something, anything, somewhere, then the difference will eventually go arbitrarily to the left or arbitrarily to the right. And in that case, there is some kind of speed, and it has linked with Lyapunov exponents. There are many things interesting things to understand, but it's not yet completely understood, this kind of cellular automata. Can I show you? Okay. This is the smallest universal cell. Okay, it's a bit stupid to make it. The space-time diagram of the smallest intrinsically universal cellular automata. So it's something that is programmed to simulate every other cellular automaton, if possible. I can give you formal definitions, but maybe not now. Okay, this is the maybe I have to. This is a cellular automaton which simulates the collapse function. You know the collapse function? It's some number theoretical, I don't remember the definition, but it's some number theoretical problem where you don't know if you start from any number like this. Here it's written in binary, maybe not in binary, in some base. And the cellular automaton applies some multiplication and some numerical operations, and you can do it. Many of multiplications can be done with cellular automaton by if there is no carry. If there is a carry, then you can do it with a tiling, but which is not necessarily a local rule. But for example, multiplication by 3 is basic. The carry doesn't propagate. There is a carry, but it can go only one step to the left, so it stays local. If there is no propagation of carry, you can program a cellular automaton which simulates this, and basically the collapse conjecture. So you have to imagine. So you have to, because it's storied, so you would have to follow this. And the collapse conjecture tells you that this successive application of this fine map always brings you to a trivial thing, and you can look at this on cellular automaton, and on everything that we tried, it was true. But we cannot prove the conjecture for maybe some Turing machine. There is this problem of
But it's difficult to compile. any normal program which this machine.
Sorry?
I suppose it's difficult to compile for this.
For this software?
For automata in general.
Why?
Because the gig, for instance, is sometimes compilers for machines without instruction logs. Sometimes they're called ancient.
Well, I don't know. So, this is a simulation of the best. There is this problem, Busy Beaver, which consists in finding the Turing machine that works for the longest time before stopping. For a given number of states and a given number of symbols. Here there are 3 symbols and 4 states, which is not very long, and you can build a program with only 4 states, which stops on empty input and which runs for 120, I think 120 or 100 steps before stopping, which is not obvious at all. And the function which to each n and to each m gives you the maximum number of steps for a machine to stop with, which is defined on n symbol and m states. This function grows faster than any computable function. So it's not computable, but it's not computable. It's faster than any computable function. Whatever program you can write to build a sequence which grows very, very fast, you know that this function will grow faster. Because if it was growing shorter than a computable, if it was growing asymptotically less than a computable function, you could write a program with this computable function and which tries every Turing machine with this number of states and symbols up to the number of steps which is equal to this program, to your computable function, and at the end you would know whether your machine halts or not. So it would contradict the halting problem. This is an example of the. So it's not very impressive, the champion with 4 states, but if you get to 5, I think it is.
Is it computed for any other points, any other symbols and states? For how
No.
much?
I don't know the current state of the art, but some people are very.
Is it 5 or like 10s or 1000s?
No, it's maybe between 5 and 10, I would say. Some people make fun and have experiments, but it's impressive. So this is not very impressive because it's a stupid example just which was easy to program. But if you find there are things that turn with 5 states that turn for thousands and thousands, millions of steps, and after a while they stop, and it's not. Of course, you can always write something which never stops. It's not the question. We want something that stops, but after a step, in some sense, this number of steps is encoded in your machine at the beginning, because it will know, without any input, it will know that it has to stop. But this encoding is not a computable map. Maybe one last one. Yes, of course, I know which one I can show you. We are talking about Turing machine, and there is this problem of the Langton's ant. I don't know if you heard about it. So here is the ant. It's in 2 dimensions. It's like a Turing machine, but instead of having a rule which tells it to go left or right, it has a rule which tells it to either to go up, down, or left and right, depending on what it reads. And here the rule is very simple. The rule of Langton's ant. When I'm in a cell, if I see gray, I put green and I go to the left, depending on my original orientation. And if I see green, I put gray, and I go to the right. Very simple rule. And we start from empty input, and it does some very
So it never goes up or down?
And then after a while, it gets into a periodic. Sorry, what did you say?
You said you go either left or right?
Yes, but left or right, depending on
Depending on
our
your
orientation.
yes,
So if remember that you arrive here, then you go to the left, but here I go either here or here. It's not a, okay, but what is strange is that this number of, so what's the number of steps here? 14,000. So, okay, this again, it does something that we don't understand at all. It started from an empty input, so all of this picture was encoded in sometimes in the definition. And after a while it does this, after 10,000 and so. So this is a big open question, of course. It's not an open question for this input, for this initial configuration. We see that it's doing this, and it's not. But the open question is, we think that it does this for every finite initial configuration. So let me, maybe I can draw something. Okay, and now, no, because, okay, then there are, okay, but it's funny also, but it's not the question, but at the beginning there were several ants, and then they met, and one of them only survives. It's not the original problem, but okay, here it works. Let's just introduce something. You see that this program as a torus. Okay. Sometimes it's very, very quick, and sometimes, okay, it came to a period. And one last feature which is interesting with this, but I don't know if I will manage to do it. Here I have the ant, and I click on it to turn it. And it goes back and it erases everything it did before. I didn't. Okay, it didn't work because I probably didn't turn it in the good way. Let me try again. There is a way to turn it by 90 degrees. So that it erases the whole picture it did. Why doesn't it work? Okay, there is a way.
What if it was periodic? Will it still erase?
Yes. Let's wait until it's. I don't know, because it started to learn from it. Okay, let's. One last try. But I never remember which way you have to turn. Okay, I got into the periodic thing. Let's try like this. No, it's rubbish. Okay, one very last. Otherwise, I will give you the address where you can download this and you can try. And there are many other examples which you can get stuck on in the. Which is this maybe? maybe I should, because I'm turning it and I change the gray to green, but maybe I shouldn't do this. Let's not change. Okay, you will find it. Yes. So what is good in this software is that you have, also in Goli, you have a lot of examples that are pre-programmed, and sometimes you can watch them and say, we don't understand anything, but so it's very nice. Okay, so tomorrow, I don't know if you want to, what you want to do. Maybe you can go through some of the corrections.
Maybe not corrections, but unsolved problems. Problems that we didn't solve.
Okay. Maybe not all.